Meanwhile, since the discontinuous output voltage waveform stops at pi, hence the equation of both voltages change as follows. Please take note of the new range of the integral functions in both equations. Let's solve this example question together. From the statement, we do know that the RMS three-phase supply voltage is 400 volts and the three-phase control half-wave rectifier is supplying 10 ohm resistive load. And the average output voltage of the rectifier is 70% of the maximum average output voltage of the rectifier. Based on the statement, we need to find the value of the average output voltage before we can solve the questions. To work at maximum condition, the control rectifier must generate the same output voltage waveform as the three-phase uncontrolled rectifier. It can be achieved when the control rectifier works at zero firing angle. Hence, by using the voltage equation, the maximum average output voltage of the control rectifier is equal to this value. Eventually, we can calculate the actual average output voltage of the rectifier. Subsequently, we can use this value to determine the delay angle or the firing angle of the rectifier. However, to determine the firing angle or the delay angle, we must know the operating condition of the rectifier. It is because the equation of the average output voltage changes according to the operation condition. Initially, we assume the rectifier operates at the continuous condition. Thus, the firing angle calculated here is known as the normalized firing angle. Based on the normalized firing angle, we know that the rectifier is actually working at the discontinuous condition because the value is higher than 30 degrees. Thus, by using the actual voltage equation, the firing or delay angle of the rectifier is equal to 47.735 degrees. Next, we can calculate the efficiency or rectification ratio of the rectifier using these following calculations. And eventually, the rectification ratio of the rectifier is equal to 70.44%. Now, let's discuss the principal operation of a three-phase controlled full-wave rectifier with resistive load. As usual, a control signal will initiate the operation of the thyristors. At the top group, the thyristor with the highest potential of the anode terminal will start the current conduction. Concurrently, at the bottom group, the thyristor with the lowest potential of the cathode terminal will start the current conduction. At this moment, the firing angle is equal to 0 since each control pulse is located at every commutation lines. Therefore, the voltage and current waveforms presented by the graph are similar to the voltage and current waveforms of a three-phase uncontrolled rectifier. When the firing angle increases from 0 to 15 degrees, it will shift the conduction range to the right by 15 degrees. As a result, it changes the wave shape of the line currents and output voltage and current waveforms. Based on the output voltage waveform, we can derive the average and RMS output voltages as follows. For your information, these equations are valid for firing angles within this range only. Lastly, we will discuss the effects of large inductive loads and source inductance on the voltage and current waveforms of the three-phase controlled rectifiers. This graph shows voltage and current waveforms of three-phase uncontrolled half-wave and full-wave rectifiers with large inductive load. Due to the highly inductive load, we can see the rectifiers are supplying a constant and ripple-free output current.